Hey, welcome everyone. So we'll continue the theme of graph algorithms, and Ali will tell us about streaming algorithms for connectivity augmentation problems.
Hello, everyone, and thanks for coming to this session. So I'm going to talk about the streaming algorithms for connectivity augmentation problems and more generally network design problems. And it's a joint work with Tse Michael Kapralov, and Sapida Mahamati. Okay, first let's see what the connectivity augmentation problem is. So I mean, as its name suggests, we would like to increase the connectivity of a given graph by 1. So more formally, we assume, what we call K connectivity augmentation problem, or K-cap. We are given a K minus 1 edge-connected graph G. And then we receive a set of weighted links. So these are basically the extra edges that we can use to increase the connectivity. And these links have weights from the set 0, 1 up to W. And the goal is to find the minimum weight subset of them, such that if we add them to the original graph, then it becomes K edge connected. Okay. For instance, this is an example. So the black solid edges are the edges in the original graph. So in this picture, they're just a tree, the one edge connected. And we can use the orange dashed edges to increase the connectivity to 2. Okay. Then, for instance, if I pick these red edges, red links, basically, then the resulting graph becomes 2-edge connected. Okay. I mean, this is a well-studied problem, for instance. Minimum spanning tree and tree augmentation problem are just special cases of this problem when we set K equal to 1 and K equal to 2. Okay, and more generally, I mean, this is just increasing the connectivity by 1. More generally, we can think of a survivable network design problem, or SNDP, where we are given a graph G with weights on its edges from, again, let's say containing 0, 1 up to W. These are the weight values. But besides that, we also given a connectivity requirement, R, which basically shows how many edge disjoint path I would need for between any pair of vertices in the graph. And the output is the minimum weight subgraph H in G that satisfy all the connectivity requirements. So basically, H should contain R of ST edge disjoint path between any pair of vertices S and T. Okay. I mean, this is a general problem. It's actually include the connectivity augmentation problem as it's a special case. And one other notable special case is K-edge connected spanning subgraph, where the connectivity requirements for all pairs is equal to the same value K. Okay. So any question here about the problem definition so far? Okay. So what are the motivation? I mean, they basically, the network design problem basically has their motivation from wireless and telecommunication network or transportation network. And they were used to actually model the reliability of the network. So the degree of reliability in the network that we have in hand, or if we want to increase it, maintain it, and so on. And besides that, I mean, even from theoretical point of view, the study of network design problem has led to fundamental advances in combinatorial optimization, algorithm, and mathematical programming. For instance, primal dual has one of its main use cases is in network design. And actually, I mean, the sequence of works on network design, in some sense, show the power of this method in approximation algorithm. Or another example is iterative rounding. And this method, this powerful method, was actually introduced to get a tight approximation for network design problem by Kamal Jain. And even even in recent years, I mean, there are lots of advancement in just special cases like tree augmentation problem and connectivity augmentation problem. And we have seen just in past maybe 3 or 4 years, there are many excitement about this problem. Okay, so what we know before going to the streaming setting, let's see what we know about it offline. So for general network design problem, as I mentioned, there is a iterative rounding approach of Kamal Jain that gives to approximation. And somewhat surprisingly, this is the best approximation that we know for this problem, and even for many of its special cases. And it was actually the case for connectivity augmentation problem till very recently. But now we know there are better approximation guarantee for connectivity augmentation on unweighted and weighted case both. So this is a very recent result in a sense. And we know that these problems are APX hard. Okay. So, but now, the topic of this talk is to study this problem in a streaming setting. So first, to make sure we're all in the same page, what we are considering is graph streaming model, meaning that the edges are coming in the stream one by one in an arbitrary order. And our goal is basically to use sublinear space in terms of the number of edges, which here is basically n to the polylog n space. It's also known as semi-streaming model. So we are considering semi-streaming model. And we are studying network design and streaming in a sense, to capture this reliability of larger scale networks. And it's a computational model for increasing that, or basically finding a reliable network in larger scale setting. And unlike many graph problems that you have seen streaming algorithm in this workshop or in general in the streaming literature, like minimum spanning tree matching, COTS, and so on, not much is known about the complexity of network design problems, or in particular connectivity augmentation problem in streaming. Maybe the closest one is testing the connectivity of the graph, which is basically you want to check whether a graph is k-edge connected or not in the streaming. But not much is known in general for this problem. Okay, so now let's go deeper into the modeling. So now that we want to study connectivity augmentation problem, there are two natural ways of thinking about it in a streaming model. First is link arrival streams. So what it means. So as I mentioned, we are given a graph G, which is already k minus 1 edge connected. And we want to increase its connectivity. And so it's natural to assume that we already have it somewhere in our system, right? So the graph is already in our system. So, and we don't need account for its space anymore in the streaming setting. Okay, so this is what we call link arrival stream. So basically, we only assume that the links are arriving in the stream, one by one in an arbitrary order. And the original graph is already stored in our memory. Okay, so for instance, here it's the graph that we already have it, and links arrive one by one. And I need to choose from them. Okay, and just some notes about, assuming to have the graph in the memory. We have very efficient compact representation for our purpose of augmenting the connectivity. One is just a simple k-edge connectivity certificate that is just union of k spanning forests and uses only order of nk edges. And the other one is the more careful representation known as cactus one, that basically preserve all min cuts and requires order n space. And the other setting is just fully edge arrival stream, that we assume that everything arrives in the stream. Both links and edges are arriving in the stream. And they can be in an arbitrary order. Okay, just to remark, this link arrival stream is only for connectivity augmentation problem, because it only makes sense over there. For the general network design problem, we always assume edge arrival stream. Okay. Any questions so far about these two models? Yeah. You can. You should store it, but you can later discard it if you want. So it's a streaming setting. Yeah, you can.
Did you consider that as part? Like you mentioned that at the end that you were computing the solution, right? I'm asking, when you see the edge, is it are you also telling in an online manner that this is part of that solution?
No. It could be just at the end of the stream. I mean, in many of cases, I'm actually just collecting a summary, and then at the end, I compute the solution. Yeah, this is a good question. So maybe key difference between a streaming and online setting. Yeah.
Is it clear that a cut sparsifier is enough to give you to solve this information once you have additional links?
Cut sparsifier, you mean here?
Yeah.
Yeah, for our purpose, I mean, basically, yeah, it's also somewhat well known that connectivity augmentation is the same as cactus augmentation. So once you have the cactus, I mean, that's enough. Because, I mean, it's preserve all the information about all cuts that you need to cover. You only need to cover the min cuts. If, you know, it's already k minus 1 edge connected, you only care about the cuts of that value. And that is preserved in cactus. Okay, so let's go. So let me tell you about the results. Yeah, it's about, I mean, I will describe the one on the connectivity augmentation and general network design. Okay, so for connectivity augmentation, we design a single pass streaming algorithm. So first I talk about link arrival model that achieve a 2 plus epsilon approximation, and the amount of space that it needs is n over epsilon times log n. Okay, and we also show that to get any approximation better than 2, you have to pay n square bits in the memory. Okay, and moreover, I mean, even if you're okay with losing more in the approximation factor, you still have to pay omega of n in the space. So in some sense, this is somewhat the best you can hope for, 2 plus epsilon, and the space is just O tilde of n. Okay, and just an interesting notice here is that, so basically this shows that unlike the offline setting, the 2 approximation actually is the barrier here in the link arrival stream. Okay, so this was for link arrival stream, and for the edge arrival stream, we show that there exists order t approximation for any integer value t that only uses order of nk plus n to the 1 plus 1 over t many edges or space. And that's actually ties, I mean, in terms of the bits. Okay. And I just want to emphasize, in edge arrival setting for connectivity augmentation, one interesting special case is when you first see all links, and then you will see the underlying graph that you wanted to increase the connectivity on it. So basically, once you see the links, you should be able to find some sparsifier so that later on you can use them to increase the connectivity for any given graph. Okay, so basically here, I mean, assume that you first see the orange links and then see what graph you need to augment the connectivity for. Okay, so that's an interesting case. And just also want to mention here that if you look at these terms for the upper and lower bounds, these complexity, they have 2 terms. So one is nk and the other is n to the 1 plus 1 over t. So the nk part is coming from the compact representation that we need to keep for the original edges in the graph. Okay, this is basically this k edge connected certificate one. And the other one, if you see more carefully, I mean, there's OT approximation n to the 1 plus 1 over t. It resembles the spanner, right? And that's indeed the case. I mean, we show that a spanner is the sparsifier for connectivity augmentation problem. And this become more apparent. Okay, so now that we know that the spanner is very critical for connectivity augmentation in a streaming, we also improve the result for weighted spanner in a streaming. So what we know about the spanner, the unweighted case, I mean, there's some classical algorithm that are already tied. So we know that order t spanner requires n to the 1 plus 1 over t many edges, and we can also make it in streaming setting easily. But the existing method, or just the standard thing for the weighted case, requires that you consider basically edges into log W partitions based on their weights, where W is the maximum weight, and then keep a spanner for each weight class separately. And this will lose a factor of log W in the space. And this is basically in the number of edges that you need to pick. So basically, for us to get the tight bounds for connectivity augmentation problem and actually for weighted spanner problem itself, we studied whether we can get rid of this log W factor and replace it with log N. And we show that actually it's possible. So we show a streaming algorithm in one pass for weighted spanners with distortion order T, for which the number of edges that we need to store is n to the 1 plus 1 over T, or tilde of that. And we know that by Erdős-Gerth conjecture that this is actually tight. I mean, any spanner should have that many edges. OK. And our result, and then we use finally our results from the connectivity augmentation problem to show the first streaming algorithm for network design problem. So in particular, for survivable network design problem, we give a single pass streaming algorithm that achieve order T log K approximation and use K times into the 1 plus 1 over T space. And we show that any order T approximation algorithm requires omega of n to the 1 plus 1 over T bits. This directly follows from our lower bound for the connectivity augmentation problem, since the connectivity augmentation problem is just a special case of network design. OK, and further, I mean, we use also, if you're familiar with this augmentation framework, we directly use our results for connectivity augmentation to show a different streaming algorithm for K-edge connected spanning subgraph, which is basically go through K passes and get approximation order log K in a space nk times log. OK, now let's see some of our algorithms. I try to describe the high-level ideas. So, I mean, the techniques for weighted spanner and connectivity augmentation are similar, but I'll tell them in the context of a spanner, since it's simpler to state that. OK, so let's see what the problem is. So we are trying to solve the weighted spanner problem. So we are given an edge-weighted graph G, and the weights belong to sets 1 to W. And we are also given a distortion parameter T. And now we would like to find a subgraph H in G such that for every pair of vertices U and V, the distance between U and V in H is not more than T times their distance in the original graph G. And we would like to find the minimum size such subgraph. OK. I mean, there is, for unweighted case, there is a very simple greedy algorithm. We start with an empty graph and just go over the edges one by one and add an edge to the spanner if it doesn't form a cycle of length order T. I mean, it's a very simple and also a streaming-friendly algorithm, and it's a space complexity is n to the 1 plus 1 over T. And if you want to actually run this greedy algorithm for weighted case, you need then the order of processing edges matter. You need to order them in the increasing in their weights. So it's not really a streaming friendly, but instead you can partition the edges according to the weight into log of W classes, and then keep a spanner in each weight class, and then you will get a spanner construction. So that simple technique will give you basically somewhat simple streaming friendly algorithm with a space complexity now order n to the 1 plus 1 over T times log W. And now, as I mentioned, we would like to get rid of this log W and have only dependence on log N. And this is what this is where our techniques come to the play. So we used even odd bucketing idea. So the standard partitioning partition the weight classes into log W partitions. But in even odd bucketing, we use basically a larger partition in some sense. So basically, we work with buckets, and each buckets now, now in each bucket, the edge weight differ by a factor of n. OK, so it's a larger interval. For instance, in the ith bucket contains all edges with weight between n to the I and n to the I plus 1. OK, so why it's useful? I mean, the key property is that now it's cheaper to pick n edges from bi minus 2 than to pick a single edge from BI. Okay, that's a very useful property for us. And it's actually lead us to try to solve the problem separately on even buckets and odd buckets. Because then I will have this property for all buckets that I'm considering. Okay, so let's say if I is even, first I just consider the edges in even buckets and try to find a spanner over them. And then I consider the odd buckets and find a spanner over them and combine them. So this is basically what I'm going to do. Find a spanner on even and odd buckets separately, and at the end of the stream, I just combine them. Okay, so let's see how it works for even buckets. And it's similar for the odd buckets. So okay, so consider even buckets, and in particular, consider BI. I'm trying to understand what edges in BI do I need to maintain in my summary or a spanner. Okay. So, and again, I use that property. For any edge UV in BI, if there exists a UV path in lighter buckets, meaning bucket BI minus 2 till and below, if I can find the path only using those edges, then I don't need to keep UV. Because I know, I mean, even picking n edges from them is cheaper than any edge in this bucket, and a UV path will has length at most n. Will have length at most n. Okay, so that's the thing, and this will actually tell me that okay, we only need to deal with the edges of this bucket BI that are between two different connected components of the induced graph by the edges of bucket I minus 2 and below. Okay, that's the main observation here. So basically, to decide which edges from BI I need to pick, I compute the connected components using the smaller buckets, and only pick the edges that are between two different connected components. So I get rid of these edge variances. And if you look at it more carefully, we also don't need to keep multiple edges. We can only keep the lightest one between two different connected components. Okay, so this basically then allow me to just contract the connected component in the induced subgraph by the edges in bucket BI minus 2 and below, and then try to try to maintain a spanner over them using edges in bucket BI. I call these nodes super nodes. I mean, these contracted nodes. Okay, so now that we're here, I mean, since let's assume that I have X super nodes in BI, meaning, I mean, the contracted nodes using the edges in BI minus 2 and so on and below. Then the spanner size would be just X to the 1 plus 1 over T. Okay, and now I can just use the simple weighted spanner algorithm that has log W dependence for the edges in BI. Why? Because now the difference between the weights of any of edges in bucket BI is just order n, and log W becomes just log n, and which is fine for us. So this is what we are doing. And if we are more careful, actually, we don't need to pay the number of super nodes to the 1 plus 1 over T here. We only need to pay the number of non-zero degree super nodes to the 1 plus 1 over T. And this is somewhat useful for our analysis. So basically using this fact and the nested structure of the connected components in this bucketing system, we can show that overall the number of edges that we are picking is n to the 1 plus 1 over T. And we are just using the log n factor because of this step. Okay, so that was basically the overview of the offline algorithm. And just I'll tell you about its implementation in the streaming. So basically, the main challenge now is that as edge arrive, then the connected components for the buckets that the edge belong to and the heavier buckets will change. And we need to basically restructure everything again. And to do that, I mean, what we really need to keep is the supernodes. And even we don't need to really explicitly maintain them or store them. We can just compute them whenever we need them once we have the graph edge. And for any for any bucket pi, we can just compute its supernodes. We can just get rid of the heavy edges and compute the supernodes. And similarly, I mean, the important thing here is that once an edge is added to this spanner, but once, for instance, I decide to keep an edge E that belongs to Bi, I need to sparsify all spanners in the heavier bucket as well. And that can be done in a streaming. OK, let me just tell a few words about, hopefully, connectivity augmentation as well. So yeah, so we were focusing on weighted connectivity augmentation and streaming. As I mentioned, two streaming model. One was edge arrival stream. And for this setting, actually, our algorithm for weighted spanner directly imply an algorithm, actually a tight algorithm for connectivity augmentation problems. So I'll skip this part. But for the link arrival stream, it's a bit different. So there is no black box reduction argument here. So we use a similar even odd bucketing idea, but now we need to deal with more involved structures. So our algorithm was a two approximation algorithm here for connectivity augmentation. So and the way we do it is that we use the fact that the connectivity augmentation reduces to cactus augmentation. And then we use another observation that actually to perform cactus augmentation, it suffices to do cycle augmentation. So it's much simpler now. OK, so just to give some idea, if I don't care about the log W factor, then that would be very easy. I only need to be able to solve the unweighted case and then blow up the space complexity by log W. So let's see how the unweighted case works. So I want to solve cycle augmentation, and the graph is unweighted. So I'm given a cycle. I mean, it's a two-edge connected entity. And I also receive a bunch of links, and I need to decide from them to increase the connectivity to 3. OK. So what are the cuts that I need to care about? So basically, if I remove any two edges, I need to make sure that the graph is still connected. So meaning that I need to have some links crossing this cut. OK. OK, so the offline algorithm, the two approximation offline algorithm works as follows. Pick some arbitrary root node. And then it shows that it suffices to only, for each vertex P, to only keep two of its incident edges that their other endpoints are closest to this root node from each direction. So for instance, here, if P has these 4 edges, I only need to keep these 2 solid green edges. That suffices. Basically, one can show that this information suffices to get a 2 approximation. It's another very involved argument, and I would be happy to talk about it offline. So basically, what it says is that you only need order of n many edges to get a 2 approximation algorithm. OK. So we would like to implement it in a streaming, but now again, instead of partitioning, we are applying even odd bucketing. But now things are a bit complicated because as opposed to the spanner that we only work with the connected component and we could shrink them just easily here, we need to deal with the 3-edge connected component. And the difficulty is that once we shrink them, then the underlying problem is not cycle anymore. The underlying graph is not cycle anymore. So we have to augment the connectivity for a different object. But still, we can show some nice structure that can be useful, that can be sufficient for us to solve this problem. OK, so I'll skip this part again. And I won't have enough time for the general network design problem, which is, so let me skip and go to the conclusion part. So basically, we studied the network design in a streaming and show that there is some nice connection between network design and weighted spanners. And That's actually the somewhat tight connection here. And so we provide some tight bounds for many network design type problem, but there are still some interesting problem for which there is a gap. So for instance, for the general network design problem and K edge connected spanning subgraph, there is a gap between upper and lower bounds. So as you see here, there's a T log K and order T, and there's also a difference in the space complexity. So I mentioned that we have tight bound for weighted K edge connectivity in link arrival stream, but the situation is different for unweighted case. For unweighted case, we still have a gap. So the best upper bound that we have is 2 plus epsilon approximation is O tilde of n. But the best lower bound that we know is basically ruling out getting better than 1.409 approximation in O tilde of n space. So there is a gap here. Just want to say, I mean, interestingly, it still says that there is a gap between the approximability of this unweighted K cap in a streaming and offline setting. Because in offline setting, we have better than 1.4 approximation for unweighted K cap. Maybe another interesting question is to study this problem in dynamic streaming. So if I allow for edge removal, edge deletion, then what would be the complexity of the problem? I mean, our approaches actually really relies in the fact that, I mean, edges are only going to be inserted. So it requires different techniques. Yeah, thank you.
Any questions?
I'm reading, even for unweighted spanners in a stream, can you do it if the edges are being removed?
Yeah, there's a work by David and Michael that they can do it.
Okay. So, do you know what's known in the offline case regarding approximately
For which problem?
big one?
Yeah, I mean, so for
Let's say the
K cap. Yeah. K cap. I mean, there was some very recent result by Vera and Rico, and they showed that actually for weighted K cap now you can get 1.5 plus epsilon approximation. So, but I mean, maybe till just 3 years ago, the best one was 2 approximation coming from Kamal Jain's iterative rounding. And there was some very recent result on this stuff.
I see. What was called lower bounds?
It's just APX hardness.
Some very tiny.
Yeah, it's just something like tiny approximation.
For the lower bound you mentioned here, 1.4, what's the dependency on K? So does this lower bound works for K equals Q?
For, I think so, actually, it's for K equal to, yeah.
And up bound is for anything, any constant.
I think it's, I think the lower bound is for K equal 2. Yeah, I don't know the exact dependence on K. Yeah, that's a good question. It's actually this lower bound is from the matching in a streaming by Michael. So we show that there's a reduction from this problem to matching.
Okay, so let's take any further questions offline. And thank Ali.
Thank you.